Swayam Prabha. Digital India. Educated India.
Welcome. Today our topic is Relaxor Ferroelectrics. Earlier we have discussed in quite a great details about the normal ferroelectric material based on perovskites, particularly barium titanate and so on. So, they are known about as normal ferroelectric materials. There are another group of ferroelectrics having many similar properties that of normal ferroelectrics, but they are named as Relaxor Ferroelectrics. We like to look at it, what are their characteristics, what are the compounds and why they behave slightly differently than the normal ferroelectric materials. To introduce this group of materials, Relaxor ferroelectrics are a group of compounds which also have spontaneous polarization like other ferroelectric ceramics. One of the basic characteristics of the ferroelectric ceramics or ferroelectric material is their spontaneous polarization even in the absence of an electric field. So, these ferroelectrics called the Relaxor ferroelectrics also do have the same property. However, their dielectric behavior is quite different from those of the conventional ferroelectrics. We look into that, how the dielectric property changes as a function of different parameters, which this behavior is slightly different than that of normal ferroelectrics. It may be interesting to discuss about these compounds and their properties. So, we will devote this particular lecture on this discussion. To start with the types of Relaxor ferroelectrics, there are different groups of Relaxor ferroelectrics. They can be classified under different groups. Based on the composition and crystal structure, Relaxor ferroelectrics may be classified under different groups, primarily 3 different groups. One is called the B-site substituted perovskites. As you remember that perovskites have the general formula AbO3. So, this is what we call the B-site substitution, that means B atom here can be substituted by some other ions. As for example, one of the very important material or most common material to have Relaxor ferroelectrics behavior is called PMN or the lead magnesium nugget. Okay. So, where A site is occupied by lead and B site you have 2 different ions, one is magnesium 1/3 and niobium 2/3. So, B site is occupied by 2 different cations, one is the magnesium ion and the niobium ion in a particular ratio. In addition to that, you have another kind of Relaxor ferroelectrics called A site substituted perovskite compounds. Okay. So, not only in B site, which has been quite common, and PMN is one of the major and the most important member of this group. The A site substituted perovskite compound is PLZT, where it is again a solid solution. We have discussed this particular compound in greater details as a piezoelectric material, a very important piezoelectric material PZT, but here it is not pure PZT, lanthanum has been used as a substituent as a dopant. So, lead, part of the lead has been substituted by lanthanum. So, the formula is as follows: lead 1 minus 3x by 2 LiX, and then Ti 0.65, Zr 0.35 O3. So, it is about, that is not in the morphotropic phase boundary, but it is away from it, and it is 65 mole percent of lead titanate and 35 mole percent of zirconium titanate, sorry, lead zirconate, I am sorry, 65 mole percent of lead titanate and 35 mole percent of lead zirconate. These two forms a solid solution, and in which part of the lead is substituted by lanthanum. So, that forms PLZD. We will discuss these things, the properties and how they are prepared at a later within a few minutes. And a third group comes not exactly on perovskites, but a derivative of perovskite structure, which is a tungsten bronze structure, and that tungsten bronze based compound in which basically it is a niobium based tungsten bench, that is Nb10O30, and added to that we have strontium and barium in some proportion. So, strontium has been substituted for barium in certain fraction, and then the total compound or the total formula becomes strontium X barium 1 minus X 5 Nb10O30. So, these are the three main groups of compounds. There are a large number of compounds available in these, under these three categories, and all of them have so called Relaxor ferroelectric behavior. Now, what are the basic differences? What are the basic differences between normal ferroelectric material and Relaxor ferroelectrics? There are 3 or 4 main points or main points of difference. Let me look at it. Relaxor ferroelectrics are different from normal ferroelectrics in several ways. First one is, similar to normal ferroelectrics, their dielectric permittivity goes through a peak at some temperature equivalent to Curie temperature. So, if you remember the dielectric behavior of barium titanate, which is a representative of normal ferroelectrics, it goes through a peak at the ferroelectric paraelectric transition, that is its Curie point, Curie temperature of around 120 degrees centigrade. There the dielectric permittivity or the dielectric constant goes through a peak and it becomes infinity following the so called Curie-Weiss law. Similar thing happens here also. At certain temperature the dielectric peak does go through a peak when you plot as a function of temperature, but unlike normal ferroelectrics, the peak temperature is frequency dependent. This was not the case when in case of barium titanate. The frequency is independent of frequency. The Curie temperature or the peak temperature is independent of the frequency, but here one of the major difference from that group of ferroelectrics to this Relaxor ferroelectric, that it is dependent on frequency. The peak temperature shifts to higher temperatures with increasing frequency. So, as the frequency increases, the peak temperature also increases. This is unlike a normal ferroelectric, or it really does not follow the so called Curie-Weiss law here. And these are the two pictures or the two diagrams showing this difference. This is normal ferroelectrics, where it goes through a peak, a very strong peak, a very sharp peak at around 330 Kelvin, this is of course 1 by epsilon prime, a straight line, whereas here this also goes through a peak, okay, but one can see the distinction between this peak and this peak. This peak is a very sharp peak and this peak is a broad peak, is a blunt peak, and not only that at 3 different frequencies, this is 100 hertz, 1 kilohertz and 10 kilohertz. Okay. So, the peak temperature shifts from this is nearly about 330 to around 360. So, there is a shift in the peak temperature. The same is of course reflected in the epsilon double prime as well. Okay. So, this is epsilon double prime and this is epsilon prime. So, there is a broad peak, and that peak also shifts with frequency. These are the two very important difference from the normal ferroelectrics, which is a very sharp peak and it is independent of the frequency of measurement. The second point of difference is, unlike normal ferroelectrics, the spontaneous polarization does not suddenly become 0 at the Curie temperature, but changes slowly with temperature. Consequently, the area of the hysteresis loop decreases also very gradually, slowly, not suddenly at the Curie temperature. Okay. Once again, these are the comparison, the hysteresis loop, how it changes as a function of temperature. So, this is the well, before the change of as a function of temperature, how the hysteresis loop at all look like. They are much broader hysteresis peak for the normal ferroelectric like this. Of course, this looks like a square hysteresis, square loop hysteresis, not necessarily it will be a square loop hysteresis, but the coercive field is large, okay, and there is a very distinct remnant polarization here. Compared to that, a relaxor ferroelectrics, there is also a hysteresis loop, but it looks like quite different. Okay. This very not only the width of the hysteresis loop is much smaller. So, the coercive field is much smaller, as well as the remnant polarization is also very small. So, it looks more or less like a nonlinear dielectrics. Okay. So, although there is a small hysteresis loop, so because of the spontaneous polarization. So, there is a spontaneous polarization, but that does not give a very broad hysteresis loop. Not only that, this spontaneous polarization in case of a normal ferroelectrics actually till very close to the Curie temperature, the normal ferroelectric has a constant spontaneous polarization, is more or less constant, and then suddenly drops at the Curie temperature. So, this is the Curie temperature where it suddenly drops, whereas we look at the variation of the spontaneous polarization as a function of temperature in relaxor ferroelectrics, it actually is a much shallower change, a much gradual change, and not only that, beyond it remains beyond the Curie point. Okay. It just does not come to, this is the so called Curie point. In fact, it is not, does not follow exactly Curie-Weiss law. So, this temperature is not always called the Curie point, although there is a peak in it, peak of dielectric constant at this position, but normally it is referred to as Tm. Tm it is something like a glass transition temperature, okay. Glass transition temperature kind of situation where you have the spontaneous polarization beyond that also. although it goes through a dielectric peak, but it is not the end of the ferroelectric behavior. The ferroelectric behavior continues beyond that temperature and is much more a gradual change for a particular value of spontaneous polarization. It will go very gradually to 0, not a sudden change in polarization at the Curie point. Consequent to this, you have a slow change in the hysteresis loop. As such, of course, is a much more magnified view of this situation. Okay. So, at away from the Curie temperature or the transition temperature here, you have a much broader peak and slowly it changes to almost a line like behavior, a non-linear behavior. Okay. So, this is a much more slow change compared to the normal ferroelectric. So, this is the second characteristics. Then you have a third variation point of variation deviation is the ferroelectric to paraelectric transition is not a first order transition. Okay. In fact, the first order transition, any first order transition will be associated with a change like this, discontinuity like this, but since it is not a first order transition, it follows a more gradual change. So, ferroelectric to paraelectric transition is not a first order transition. Consequently, there is no evidence of optical anisotropy or X-ray line splitting of the ferroelectric phase. Okay. These are the two very important consequences of the ferroelectric transition of normal ferroelectric materials. Because of the ferroelectric to paraelectric transition at the Curie point, there is always a optical anisotropy, evidence of optical anisotropy from one crystal structure to another, and also is associated with a what we call a X-ray line splitting of the ferroelectric phase. Now, however, this kind of evidence is not there in Relaxor ferroelectrics. It does not have the splitting behavior, X-ray line splitting. Okay. These are all single lines, there is no double lines or splitting lines, except of course alpha 1 and alpha 2 splitting is there. But also there is another change or another deviation in the optical properties. Optical properties, there is a lot of quite a bit of birefringence, because there is a distinct crystallographic change. So, there is a lot of birefringence for the normal dielectrics, whereas here there is no birefringence. Okay. So, the optical refractive index is not dependent on the particular crystallographic direction. Okay. So, these are the another third point of difference between the normal ferroelectrics and the Relaxor ferroelectrics. And also there is a fourth which has been mentioned earlier also, the very first one when we were discussing the same diagrams. The ferroelectric to paraelectric transition has a rather diffuse characteristics, diffuse peak with a relatively broad dielectric peak arising from the disorderness of the nano sized ferroelectric domains. Well, one of the reason, a simplified way to look at it, why this kind of broad peak appears is there is a nano size domains, or the size of the domains is much smaller, much smaller compared to the normal ferroelectrics, and these are some kind of disorder structure. So, the domains do not follow a very nice pattern or nice crystallographic orientation, but it is a disorder, it is more random in nature, even when it is ferroelectric. Okay. So, these are the 4 different points of difference between a normal ferroelectric and a relaxor ferroelectric. Now, what are the different compounds? We have already seen that there are 3 groups under which all these compounds can be classified or grouped depending on that particular structure, crystal structure. Here let us look at some of the specific compounds. The first group is the so called B site substituted perovskites. So, the AbO3 structure, you have B1 and B2. Instead of B, we have 2 different atoms or 2 different ions, B1 and B2. So, these A is normally lead, that is the only possibility so far as the A site is concerned. But B site, there are different combinations are possible. B1 can be magnesium, zinc, mostly divalent or trivalent oxides or trivalent elements like magnesium, zinc, nickel 2 plus, Fe3 plus, scandium 3 plus, etc. So, either it is 2 plus or 3 plus. Consequently, B2 will be either 4 plus or 5 plus, or it can be 6 plus even. So, these are the atoms in the B site, possible atoms: Ti 4 plus, niobium 5 plus, tantalum 5 plus and tungsten 6 plus. So, these are the different ions which can be there in the B2 site or B site, and B1 will correspond to magnesium, zinc, nickel, iron and scandium, either they are 2 plus or 3 plus. Accordingly, you have several compounds here which has been listed. This we have already discussed, the PMN, one of the most important member of this group, lead magnesium niobate, then lead iron niobate is also there, EFN, magnesium has been replaced by iron. You can have PFW, this is iron plus niobium has been replaced by tungsten. Okay. So, that is also possible. Of course, the ratio is will be different to satisfy the charge neutrality. And then lead zinc niobate is also another member. So, all these compounds are actually relaxor ferroelectrics and having the 4 different characteristics which we have mentioned earlier. How to synthesize these compounds, particularly the representative one is the PMN, lead magnesium niobate. So, normally it has been prepared or it is being prepared as solid state synthesis, but other liquid chemistry route or the sol-gel route, and there are many other techniques by which the PMN, the lead magnesium niobate kind of ferroelectrics can be synthesized. Preparation of single phase perovskite PMN is extremely difficult, primarily due to high melting point of MgO. So, compared to lead and niobium or niobium oxide or lead oxide, magnesium oxide has much higher melting point, and therefore, its diffusivity is very low. Magnesium diffusivity is quite low, and therefore, you have some amount of difficulty in synthesizing this compound in the right stoichiometry. It is normally contaminated with pyrochlore phase. Well, a derivative of perovskite is also a pyrochlore phase, A2B2O7, that kind of compound, and these pyrochlore phase are not non-ferroelectric in nature. So, even the relaxor behavior is not there, and as a result there needs to be avoided during the normal synthesis route. The calcination temperature of this compound is nearly 650 to 800 degrees centigrade, whereas the sintering temperature is around 950 to 1200 depending on the particular compound used to make this relaxor ferroelectrics. So, this temperature as you can see is a relatively low temperature compared to the barium titanate. So, the sintering as well as the calcination temperature both are relatively low. So, they are relatively low melting compounds compared to barium titanate. Looking at the case of PMN, so far as the synthesis is concerned, the PMN the reaction proceeds in two different steps, two possible steps. Formation, the first step is the formation of an intermediate lead niobate pyrochlore phase. So, lead niobate, because there are three cations involved with oxygen, and their reaction rates are a little different, the diffusion rates are different. So, you have directly it does not form the lead magnesium niobate, instead the first phase which appears is lead niobate. So, it is a binary phase, a binary composition. So, it is not a ternary one obviously. So, the formation of the intermediate lead niobate pyrochlore, and it also has a pyrochlore structure, and this pyrochlore structure is little bit detrimental to the ferroelectric property of either the normal perovskites or the relaxor ferroelectrics. This pyrochlore phase in turn reacts with the excess PbO and MgO to form the perovskite PMN phase. So, initially a lead niobate pyrochlore phase forms, and then that lead niobate pyrochlore reacts with the excess amount of lead oxide and magnesium oxide to form the perovskite or the PMN structure. So, this reactions has been represented like this: PbO plus Nb2O5 goes to Pb2 Nb2O 5.5. Okay. Pb2 Nb2 O 5.5, that is the cubic pyrochlore structure. This Pb2 Nb2 5.5 or 5.5, sometimes it is written as 5 and sometimes in some cases 5.5, but it does not matter, basically it is a cubic pyrochlore phase. It reacts with excess PbO and MgO time to form the PMN perovskite structure plus pyrochlore. Now, this pyrochlore phase of course is not a very accepted second phase. So, we have to avoid the formation of the pyrochlore, or in the final phase it should not be present. To do that, to avoid the formation of the pyrochlore phase, an alternate route has also been suggested. Once again, it is solution, not solution chemistry, but it basically a solid state diffusion, solid state route. First, MgO and Nb2O5 are reacted to form a MgNb2O6, or sometimes called columbite, which in turn is reacted with PbO to form the single phase PMN. Okay. So, the pyrochlore phase, columbite phase, lead magnesium niobate, not the lead, only magnesium niobate which forms initially is allowed to react with the lead oxide, and also is allowed to react with PbO, so that it gets transformed to the single phase PMM. Okay. for completion of the reaction about 2% excess of MgO and a prolonged heating is necessary, more than 4 hours, but sometimes it is more actually, at 800 degree centigrade to ensure the formation of 100% PMN. So, its synthesis of PMN is slightly difficult because it has a tendency to form the pyrochlore phase. In order to avoid the formation of this pyrochlore phase, sometimes an addition of lead titanate is also useful to eliminate the formation of the pyrochlore phase. So, by adding or making a solid solution with another titanate, lead titanate, which is a very relatively simple one to prepare. So, some amount of lead titanate is added, and when a solid solution forms with lead titanate and PMN, the pyrochlore phase formation is avoided. In order to prepare a temperature stable dielectric with high dielectric constant of about 20,000, that is the peak dielectric constant, different compounds are mixed together and primarily to stabilize the perovskite phase. So, one example is PMN with PT, PT means lead titanate, and lead nickel tungstate, some amount of nickel tungstate is also added, which are also having a relaxor ferroelectric structure. So, this solid solution actually is sometimes used for practical purposes. The next thing is what is this origin of this particular property. The so called diffuse phase transformation is called diffuse phase transformation, and then you have a glass like structure and so on. So, what is the basic difference? So, for the internal structure of the perovskite, normal perovskite, and the relaxor ferroelectric is concerned. Extensive research of the last 3-4 decades has indicated that the presence of nanoscale polar domains. So, it is actually nanoscale polar domains, which means basically the ferroelectric domain. All ferroelectrics are supposed to have domains, ferroelectric domains of certain size and certain other characters. So, in this case also you have domains, but the basic difference is compared to the normal domain size of which is of the order of microns, so on. Here it is nanoscale domains, okay, very fine nanoscale domains, and they are not fully order structure or a fully crystallized structure. They may be crystallized, but so far as the domains are concerned, they have a disordered structure. Now, because of this disorderedness, instead of a single relaxation time, as in case of barium titanate, you have a multiple or a spread of relaxation times or a distribution of relaxation times. So, each one of them relaxed having each one of these domains have a different relaxation time, and because of that you have different relaxation processes occurring, and their time constants are also different. Because of the time constants are different, they respond to different frequencies. Okay. So, that is one of the reason why there is a broad peak instead of a sharp peak in case of normal ferroelectric. In normal ferroelectric, the sharp peak arises from the single relaxation time. So, these structures is much more order, and they have a larger domain size. Size and volume percent of these nanopolar regions vary with temperature. Particularly for PMN, these domains start forming around, if you are cooling from a higher temperature, then these domains start forming around 620 K, and their size is about only 2 to 3 nanometers. So, that is basically in the paraelectric phase, and when you cool down, so around 400 K, further increase in the domain size around 10 nanometers size of domains formed at around 160 degree K, and the volume fraction being around 30%. So, 30% of these polar domains, so nanostructure domains are formed, and that is having a disordered structure, a distribution of relaxation time, and therefore, you have a broad peak. While going to the little bit more details, there is a different theories of these phase transition or paraelectric to ferroelectric transition, and the presence of nano domains or nanopolar polarization or nanopolar structures. This has been explained by a theory or model called spherical random bond or random field model, a spherical random bond random field model, which is in brief it is called SRBRF model. Now, it says that as I have just mentioned, that we have a variations in the domain structure, and their characteristics of each of these domains are different. Not only their size are very small, but each one of them has a different relaxation time. So, the polarization can be expressed as sigma epsilon 1 minus 1 minus epsilon 3 minus epsilon 3 E, the electric field. So, normally we write this equation epsilon minus 1 into E, that is the relationship between polarization and electric field, but here because of the distribution of relaxation time, you have a different parameters or different a kind of polynomial is written as the relationship between polarization and electric field. So, epsilon 1 minus 1 multiplied by E minus epsilon 3 E, and so on and so forth. This can be written in another way, E equal to A1 P plus A3 P cube, where A3 is basically epsilon 3 by epsilon minus 1 whole to the power 4 is approximately equal to e to the power 3 by epsilon to the power 4, epsilon 1 to the power 4. In this case, epsilon 2 term is not there because of the centrosymmetrical cubic structure of PMN. So, the polarization reaction or the polarization expression or the relationship between the polarization and electric field is quite different here compared to the normal ferroelectrics. Now, this A3 parameter can be written can be determined for different PMN relaxor ferroelectric structures, and here there are two examples. They have been determined from the optical parameters or the optical measurements, refractive index measurements, and one can see the A3 parameter changes monotonically as a function of temperature. Okay. The temperature dependence of A3 in this is PLZT, as you can see this is one of the Relaxor Ferroelectrics, lanthanum doped PZT, and at a voltage of 8.5 or the electric field of 8.5 kV per centimeter square, which is greater than E 0. This A3, the A3 has been plotted here. So, this A3 parameter of PLZT at 400 hertz, the monotonic decrease of this parameter is consistent with the SR-BRF model. So, this kind of a change, monotonic change actually is an indication of the Relaxor ferroelectrics, and also it provides a clue that the actual nano size domains are present in these ferroelectrics or compounds. This is also another one, triglycine sulfide. Okay. So, this is the paraelectric phase, this is the transition phase. Okay. I am not going to the details of this analysis, except so that it gives an indication that the nano size domains do exist, which is different from that of the normal ferroelectrics. And these nano size domains actually do have different relaxation time there, and that gives rise to a frequency dependence. At different frequencies, a different set of domains becomes operative, and that is the reason one gets a distribution of the relaxation time, and you get a broad peak. The relaxor ferroelectric materials are also characterized by another very important parameter or another very important property, that is the electrostrictive property. As you have discussed earlier, that electrostrictive properties have some amount of similarity with the piezoelectric property. So, where actually as a function of applied field there is a strain, though the dimension changes as a function of applied field. So, it is more or less equivalent to the piezoelectric material. So, the relaxor ferroelectrics, particularly PMN, is known for its strong electrostrictive electro-optic as well as electrostrictive properties. Okay. The effect is much stronger than the piezoelectric effect of PZT. Okay. So, this is another very interesting property, particularly for PMN, and that was the reason, this is one of the reasons why this property has been exploited in the corrector tilt mirrors of the Hubble telescope. Okay. So, basically it is an actuator, one can use it as an actuator. In addition to a good dielectric material, one can use it as a good transducer material and actuator material. So, if you want to need a very stable actuator, that is really possible with this kind of ferroelectric relaxor ferroelectrics. In fact, one of the reasons why it is a better actuator material than PZT is its aging characteristics. Aging is a common phenomena in most of the ferroelectric compounds, whereas in case of relaxor ferroelectric, aging is negligible in phase pure, particularly pyrochlore free stoichiometric PMN, and it is much better when it is made a solid solution with 10 mole% of PT, and that is a very stable material, and it is completely pyrochlore free, a pure material, pure perovskites, of course A size substrate perovskites, solid solution, and that aging property is almost negligible. So, with time the property really does not change. However, the aging phenomena may be there once it is doped with small amount of MNO. If MNO is added, it has been found that this aging characteristic reappears. So, because the aging properties of this ferroelectric or the electrostrictive properties are negligible, they can be a good actuator material. Well, that was all about the B site substitution. The other group, as we mentioned earlier, is the A site substituted relaxor ferroelectrics, and once again this is based on the most popular piezoelectric material, that is PZT. In fact, PZT has been substituted, where some fraction of lead has been substituted with lanthanum, and of course this PLZT, lanthanum substituted PZT, has a very important characteristics, and it is one of the first electronic ceramic materials hot pressed to optical transparency. Okay. So, piezoelectric material, transparent piezoelectric material is actually PLZT, but PLZT is also characterized by relaxor ferroelectrics at a certain percentage of lanthanum. As in pure PZT, there is a morphotropic phase boundary between rhombohedral and tetragonal ferroelectric phases that we have seen earlier in PZT ceramics, while we were discussing the piezoelectric property of PZT. And at the morphotropic phase boundary, as you know, the coupling coefficient is maximum, the energy conversion is maximum, and that is the reason why we use a composition very close to the morphotropic phase boundary. Here also you have a morphotropic phase boundary, and the rhombohedral and tetragonal ferroelectric phases, particularly with low concentrations of lanthanum. So, less than 12 atom percent you do have a morphotropic phase boundary, that is the characteristics of the phase diagram. However, the typical relaxor composition in this system are about lead 1 minus 3x by 2 LiX ZR 0.65. This composition was presented earlier, and the x value changes from 0.06 to 0.12, that is about 6 to 12 atom percent. Relaxor behavior starts from about 6 atom percent lanthanum, and it increases as the lanthanum percentage increases. The dielectric peak broadens with increasing lanthanum content, and that is possibly presented in the next slide. This is the A substituted relaxor ferroelectrics, and as you can see, there are 4 different diagrams, basically schematics here. The relaxor phase is stabilized either by increasing the lanthanum or by applying hydrostatic pressure, that we will see in the next slide. Okay. So, here this is La 6 atom percent, LS this is about 6.5 atom percent, and this is lanthanum 7 atom percent and 8 atom percent. So, as mentioned, up to X can vary between 6 and 12. Here about 4 compositions have been presented, and you can see the typical peaks. This peak is about 185 degree centigrade, and you can see a slight narrower peak, whereas the broadness of the peak increases as we increase the lanthanum content from 6% to about 8%. And not only that, the peak temperature also shifts from 185 to 160 and then 135, and finally with 8 atom percent it shifts to about 115 degrees centigrade. So, not only the peak shifts, the peak also broadens quite a bit compared to this. This is a much broader peak, and not only that, you also see the peak dielectric constant is also different. Here the maximum here is about 16,000, here the maximum is only up to 12,000. So, this peak dielectric constant or K prime value is lower compared to this value. So, this is what happens, that means as such PZT, okay, as such lead zirconate titanate is not a relaxor dielectrics or relaxor ferroelectrics, it is a normal ferroelectrics, but as you dope lanthanum or substitute part of lead with lanthanum, it becomes a relaxor ferroelectrics. Now, this kind of relaxor property can also be induced or stabilized by applying hydrostatic pressure. So, not only lanthanum addition changes the normal ferroelectrics to relaxor ferroelectrics, but by applying higher pressure the relaxor ferroelectric behavior can be brought in, and that is what has been shown here. This is 1 bar pressure and that is 10 bar pressure. Okay. This is also 1 bar. You can see here it is about 6 atom percent PZT, PLZT. This is 1 bar and this is 10 bar. So, you have a much broader peak here and it decreases in the temperature range, and whereas if you have a 1 bar, it a much sharper peak with 6 atom percent, which is the lower limit of lanthanum, where one can expect the relaxor behavior. However, it becomes quite distinct when a higher pressure is used. And the third, another compound in addition to lanthanum doped PZT, there is another compound which is also in the same group, that is the A substituted A site substituted relaxor ferroelectrics. This is one thing. The bismuth substituted strontium titanate. Okay. So, the bismuth substituted strontium titanate, where part of the strontium has been replaced by bismuth, that also has a relaxor ferroelectric behavior, but the details of the data are not here. Okay. Well, the third group is this one, that is the tungsten bronze based relaxor ferroelectrics. So, the general formula here is this one, it is a slightly complicated different kind of formula, is A14, A22, C4, B10 and O30. Okay. So, there are many different compounds known, about 150 different compounds are known in this group, in this general formula. So, there are A1, A2, C and B, these are 4 different cations involved, and the molecular formula is also complex, but one can have a large number of compounds in this. The description of this structure is like this: you have A1 a 15-fold coordination, A2 is a 12-fold coordination, C is a 9-fold coordination, and B is a 6-fold coordination. Okay. So, the structure is quite complex in nature. One of the compounds, the example of this particular structure is K4 K2 potassium, it is potassium lithium niobate, all sites are occupied, all A1 4, there are 4 sites, there are 2 sites here, there are 4, 10 and so on. So, all of them are occupied. If you compare this particular formula and this one, you can see all of them are occupied. There are 2 different types of potassium ions here. One is the A1 site and there is the A2 sites having different coordination numbers. Structures are however more stable when all the sites are not occupied. So, if the some occupancy factor is little less, then the structure it seems are more stable. So, one of those structures are strontium, barium, niobium oxide or niobate. A sites are only 5/6 filled. Okay. So, out of here is 6 A including A1 and A2, there are 6 sites here, it is 5 of them are occupied. Okay. 5 of them are occupied, and that too partly it is strontium and partly barium. So, 1/6 is vacant here, and that it seems that stabilizes the structure better. So, which leads to charge imbalance, strong disorder and consequent relaxor behavior. So, basically a relaxor ferroelectric structure is a disordered structure, and you have a distribution of different sizes of nano domains, and that is the origin of the relaxor behavior of ferroelectrics. Although there is a spontaneous polarization, but it is the disorderedness, disordered structure is the key for getting this or getting the relaxor behavior. So, here also that is what, because of this vacancy or the unfilled sites, you have charge imbalance and then strong disorder and consequent relaxor ferroelectric behavior. Okay, I think that is more or less discusses completes our discussion on relaxor ferroelectrics, and also the discussion on all the different groups of dielectrics. Initially we have discussed the normal dielectrics, then we have nonlinear dielectrics, ferroelectric materials, piezoelectric materials, pyroelectric materials, and finally we have discussed the so called relaxor ferroelectrics. So, there are different groups. Before I close on this particular subject, one of the applications of relaxor ferroelectrics of course is its utilization of the electrostatic property. That means one can use a very stable as well as efficient actuator material for different kind of actuators. One of the examples which has been given is to correct the tilt correction for the Hubble telescope. It has been used, that is one of the good or great uses of relaxor ferroelectrics. But the other important application is in the multilayer dielectrics. As you can see, the relaxor ferroelectrics, particularly PMN, has a lower melting point or lower sintering temperature. It can be formed at a much lower temperature, relatively lower temperature than barium titanate, and therefore it can be used with low melting or base metal electrodes. If you are having a high melting point of 1200 to 1400 degrees centigrade, then you have to use a costly noble metal electrodes in multilayer structures of capacitors, multilayer capacitor structures like silver, palladium and so on. More amount of palladium has to be added. Palladium is very quite costly, and therefore they increases the cost. Whereas if you have a relaxor ferroelectrics like PMN, which can be sintered at a much lower temperature, so one can use either silver or copper based materials. And not only that, you have relaxor ferroelectrics have a much broader temperature coefficient, or sorry, the temperature effect or a broad peak of dielectric constant. So, it is more temperature stable. Okay. So, it is more temperature stable, and therefore, one has an advantage of using it as a multilayer capacitor or dielectrics for multilayer capacitors. So, both as an electrostatic material as well as a multilayer capacitor material or dielectric material, relaxor ferroelectrics have an advantage, slight advantage over the, and also you do not have an aging characteristics, right. So, these are some of the advantages of the relaxor ferroelectrics over normal ferroelectrics or normal dielectric materials. So, with this we come to the end of our discussion on dielectric materials, including ferroelectric, piezoelectric, pyroelectric as well as relaxor ferroelectrics. Thank you very much for your kind attention. Thank you.